Hey folks, feel free to grab some pizza and drinks in the back. We should be getting started in about 10 minutes. I just want the room to fill up a little bit more, so thanks for coming.
much this.
All right, thanks everybody for coming out tonight. Looks like folks are getting situated. If you're not sitting down, I encourage you to just grab a seat, grab a beverage if you haven't. I think there might be a sparse amount of pizza left, so you should go grab one if you're hungry, if you haven't eaten. So this is the first cloud native storage SF meetup. It was formerly the Cluster HQ meetup. Some of the pioneering folks behind container storage. It was a meetup that got sort of revived around that. So hopefully we'll be doing regular, so sort of general cloud native oriented, storage oriented meetups. And tonight we've got some really cool presentations from a couple folks in the community, from Bassam Tabara at Quantum talking about Rook, and from Saad Ali at Google talking about container storage interface. So without further ado, I pass it over to Saad. Round of applause.
All right, can folks hear me okay? All right, thanks JJ. My name is Saad Ali. I'm a software engineer at Google, and I work on Kubernetes, mostly the storage stack. And over the last year or so, we've been working on this container storage interface, and I wanted to introduce this to folks more publicly here today. So I'm gonna go over what exactly CSI is, Container Storage Interface, where it came from, what's next, how it actually works, and we'll save Q&A until the end. If you have any burning questions, just raise your hand and wave at me. So first up, the background. What were the motivations behind Container Storage Interface? And it's basically two things. From the cluster orchestration system, and when I say cluster orchestration system, that's Kubernetes, that's Docker Swarm, that's Mesos, Cloud Foundry. We as cluster orchestration systems want to be able to offer our users as many storage systems as possible. On the other hand, storage vendors want to also make their system available to as many users as possible and do as little work as possible. And today, what they kind of have to do is navigate through all the different orchestration systems, kind of figure out how to make it work with those systems. And so what CSI is it's an attempt to define an industry standard cluster orchestration system, which can be used to expose any arbitrary storage system. And you know, it's like the old joke. We just one more standard and it'll solve everything. And that's well, you know, there's a joke. It's kind of true. It might. We're hoping this is the one that will work for all cluster orchestration systems. So it is a collaboration between Kubernetes, Mesos, Docker, and Cloud Foundry. It started in February of 2017. We all got together into a room and we agreed that this is a problem that we would like to address and collaborate on together. And once we established that, we created a small working group to try to drive towards a solution. And we tried to keep that initial working group small because we wanted to keep it user-focused rather than letting it become a war between storage vendors. We believe that the cluster orchestration systems kind of have the user's best interest at heart, and they can represent the user's best interest, and they could help define this in a way that wouldn't be biased towards any single storage system. So where are we today? There's a spec that is published on GitHub at github.com/containerstorageinterface. You can go check it out. I wanted to thank G and James, who did a lot of the heavy lifting and helping actually craft the spec. And the initial version of the spec has been published, and what we're doing now as cluster orchestration systems, Docker Swarm, Kubernetes, Mesos, et cetera, we're all going back to our respective communities and saying, okay, how do we take this draft of an interface spec and actually implement it in our systems? And the idea there is that while the CSI spec hasn't gone to 1.0, we're going to go back, try to implement it, learn from that, revise the spec, and then call whatever we all agree on 1.0. So that's the point that we are at today, and where we're going tomorrow. So we can jump in a little bit into what CSI actually looks like. Let's start with what CSI is not. CSI does not define the packaging, the deployment, the monitoring of the plugins themselves. What CSI does is define the interface. And it very purposefully limits itself to that layer. Imagine it like the networking layers. HTTP doesn't really care what runs underneath it. And we want to have a very strict abstraction layer and say, this is what CSI is, the packaging you can decide for yourself. Ultimately, we do want storage vendors to be able to write a CSI compatible plugin and have it just work everywhere. So we'll need some sort of packaging. The packaging needs to kind of align at some point. But we want that to happen organically. We want the cluster orchestration systems to define that in a way that it makes sense for each of their systems and have that converge, while the spec is just the interface. We also didn't define grades of storage within the spec. This was something that people kind of confused. This is you could have gold storage or silver storage based on how fast storage is on IOPS and that kind of thing. And the idea here is we will expose the hooks that will allow cluster orchestration systems to expose that. We're not going to implement that ourselves inside the spec. We're not going to dictate it. Then let's talk about what CSI actually is. It is an interface, and it enables three major scenarios. One is creation and deletion of volumes. This is when an end user requests storage. The cluster orchestration system can go out, talk to the storage backend to have a new volume created to fulfill that request, and then when the user is done with it, have it deleted. The second is making the volume available on the machine that their workload gets scheduled on. For some storage systems, this is a no-op. So if you imagine NFS, it'll be equally available on all machines. But for some storage systems, if you think Amazon EBS, for example, there is a step where you have to take the iSCSI device and make virtual iSCSI device and make it available on a particular node. There's attach and detach. And then finally, the mount unmount step, which all volume plugins would have to implement, which would actually make the volume available at a particular path on the host machine. And so you guys are probably thinking at this point, what about all these other cool features that storage systems expose, like snapshots and replication and et cetera, et cetera. The purpose with CSI was not to be the cutting edge. It's not going to lead the way in storage. What we want to do is make it an appliance. This is the least common denominator that all of us need in order to get bare minimum functionality. And so with 1.0, we're focusing on just those three simple things. The plan is to add additional things as we agree on them as they converge. We will let them evolve in the cluster orchestration systems, and once we converge, then we add it into the spec. So what do we say to non-critical functionality? Not today. The last thing I want to add is this mount-unmount call is the one call that must be executed on the node machines themselves. The create and delete calls and the attach-detach calls theoretically could be executed from anywhere within the cluster because the storage control plane usually exposes some kind of interface and you can call it from anywhere within the cluster. But the last mile of making your storage system available to the user, that code needs to be executed on the node machine to basically make it available. And so for that reason, we kind of segmented the API into three sections. One is the controller, the second is the node, and the third is identity. With the controller, these are calls that could be run from anywhere. So as I said, attach, detach, and create and delete. With calls that are categorized as node, these are guaranteed by the cluster orchestration system to only be called on the node where the workload that is referencing that particular volume is actually scheduled. And finally, identity would be a set of calls that provide generic plugin information. So next up, let's talk about naming, because I've given you these really nice names. Create volume, delete volume, makes sense. Attach volume and detach volume make a lot of sense to me, and that's kind of what we call them in Kubernetes. But the feedback that we got was that, wait a minute, I don't have an attach call. I have something that needs to be executed to make a volume available, but it's not really an attach. And mount and unmount can actually encompass more things than just mounting or unmounting. You could theoretically apply a file system there or a bunch of other things. And so what we did was name them these big, long, funny names. Controller publish and node publish. Controller publish is the control plane attach call, basically. And node publish is the component that is going to be executed on the local machine, on the host. So the 6 main calls are create volume, delete volume, controller publish volume, controller unpublish, node publish, and node unpublish. There are a set of other calls. I can show them to you at the end of the talk if you're interested, but that's kind of the high-level flow. So if you take a typical cluster, you're going to have some sort of master control plane, and you're going to have node machines where the workloads are actually going to be scheduled. So if you deploy a CSI-compatible plugin, one mechanism for you to do that would be to have your CSI plugin containerized and running on master and node. On the master side, it would only expose the controller interface and the identity interface. And on the nodes, it would expose the node interface and the identity interface. So now if an end user goes to the cluster orchestration system and says, I want storage, it has to be 20 gigabytes, make it happen, what your cluster orchestration system will do is it'll call the controller plugin and say, I need a new volume, and here are all the parameters. It needs to have this much capacity, and I'm going to use it as a block device, etc. The plugin can then go ahead and call out to the backend storage control plane or do whatever it needs to do. Rook, which you guys are going to hear from next, does some cool things with a controller-centric model where they generate object within the Kubernetes API, and they have a controller that monitors that. So really, the implementation is up to you. Basically, whatever the storage plugin needs to do, it's going to be a blocking call. They'll go out and provision the volume and return to the cluster orchestration system that the volume is created. And the information returned is the information that is required to uniquely identify that volume in the future. And the cluster orchestration system will keep track of that, return it to the user if appropriate. And so once a volume is created, the user will want to actually use that volume somewhere. They're going to tell the cluster orchestration system, that volume that you gave me, I want to use it with this workload. Go and schedule this workload somewhere where there is availability. The container orchestration system goes out and says, okay, I know that there's some memory and CPU available on node B. I'm going to place your workload there. And now I need to make sure that that particular volume is available on that machine. So if this particular volume plugin implements the controller publish call, then the control plane will call publish volume. That should say controller publish. Here we go, controller publish volume. And it'll pass in the same volume information that was returned on the create volume call to identify that volume uniquely, along with information about which node to attach it to. There is additional calls within the interface to identify unique IDs per node, so that there's going to be a way that the storage system identifies its nodes, and there's going to be a way that storage systems identify their nodes. And so there's a call within CSI that can be used to map between what the storage system identifies and what the container orchestration system identifies nodes as, so that you can talk the same language. In this case, you use that node ID that both of you understand to say that I want this particular volume to be attached to this particular node. So then the plugin calls out to the control plane, makes that happen, and returns a publish volume info, which contains some opaque map, which is up to the controller, up to the storage vendor to determine what the contents of that is. Basically, whatever information is returned on the attach, the container orchestration system is responsible for passing back in on the node published. For the vast majority of storage systems, it may be nothing. So now that the volume is actually attached and made available on the host machine, you can imagine this as Amazon EBS device showing up as a device on the node. You need to take that device and make it actually available in a path that can then be mounted into the container. That's where the node publish volume step comes in. This is going to be executed by the container orchestration system on the actual node. And so we're going to call the portion of the plugin that's actually running on the node machine. And we're going to pass in the same volume information that we had when the volume was created to say this is the volume that needs to be mounted. The volume plugin is then responsible for making it appear at the target path. And when that's done, then the workload is ready to run and it's available inside of the container. We take the target path, we pass it into the container runtime, whether that's Docker or something else, and it's available for the user to use. Teardown is just going to be a reverse of it all. You do node unpublish, controller unpublish, and so that's pretty much it. There are a few more calls. If you guys want, I can go into details of what they are, but you can think of them as mostly supporting calls. They're not exposing any new functionality. They're kind of there to, they're the glue to make everything work together. And that's pretty much it. Short and sweet. Any questions?
Really basic question. So in Kubernetes, there
persistent volume claims.
Do
correct.
they survive after this?
Yes. Yeah.
PVCs survive, and this would just be
Right.
machines mechanism.
Exactly. So if you look at the way that Kubernetes has implemented volume subsystem today, a lot of these calls kind of mirror what's going on internally. And so while the PVC system is going to continue to exist, that's the mechanism by which the Kubernetes exposes storage to end users. What this is the other side of the system, which is currently all internal and opaque to users. We're clipping it off and saying, okay, there's a public interface by which storage vendors can plug in. The user-facing side of things is more or less going to remain the same, and only the storage vendor side is going to become more pluggable.
To
right.
create PVC.
Right.
And that's just sort of one-off.
Yeah, so for Kubernetes specifically, the way that volume plugins work is they're all in tree, meaning they are actually compiled into the Kubernetes code base. And that's very, very painful for storage vendors because either they don't want to open source, they don't want to be tied to the Kubernetes lifecycle or the release cycle. So this is the mechanism by which we're planning to go out of tree, at least one of the mechanisms. We already have flex volumes, which is an exec-based model. With CSI, we're trying to come up with something more robust. The idea would be that these volume plugins would be containerized and deployed via Kubernetes, all out to them. The volume plugins can be developed independently.
Doesn't PVC spec or something? Already?
Yes.
So then how does that?
And which is why we had that warning in the beginning of what CSI is not. CSI doesn't define classes of storage. What CSI does is it exposes, so the way that the storage classes work in Kubernetes today is that you create a storage class with a bunch of opaque parameters that get passed through on creation to the in-tree volume plugin. And so it works very nicely with this because the only thing that's changing is instead of passing those opaque parameters into the in-tree volume plugin, you're going to be passing them into some CSI external volume plugin. So the public-facing interface doesn't change at all. We still have the same classes. This is all just underlying guts kind of stuff.
How do you select the node? Do we select where to schedule the task?
Yep.
I think I missed that.
Okay. So CSI specifically does not define who selects the node. It is the responsibility of the cluster orchestration system. So if you look at Kubernetes today, we have a scheduler, And when a workload is created within Kubernetes, that's a pod, it is unscheduled. We have controllers that monitor these pods. And the scheduler says, oh, I see that there's a pod that is unscheduled. I know what resources are available on my server. I'm going to go ahead and place this wherever there's resources available. That's the cluster orchestration system.
That's why you have the second problem. Follow publish, where you say. Second, it's not a problem. Interfaces looks very. Maybe it's like some like Meetup, EMC, and other stuff. Already doing this.
Yeah.
I mean,
Absolutely. So
about it, like
I personally don't. What or the learnings that we've used are a lot from what we've already implemented in Kubernetes systems. That said, we realize we are not storage experts, and the project is public and open source. And so we want folks to come and join our community and help shape it. If there's something that's missing, join and let us know. Join the meetings.
It seems like there's what is sort of the design?
It's a very complicated system. More or less, we've kind of implemented this within Kubernetes. It's going through that. The problems that we had with Kubernetes were that we were trying to do the end-to-end system ourselves, right? The storage plugins were in tree, and the problem with that was we didn't necessarily have the ability to test a lot of these volume plugins because we didn't have the infrastructure. A lot of these storage systems are proprietary and untested. And so going from that to what this is proposing is actually nicer because as far as Kubernetes is concerned, it now has a very limited interface that it exposes. And so we would be, from the Kubernetes side of things, responsible for testing only that interface. We can stub out the plugins themselves. And then storage vendors who implement these volume plugins would be responsible for testing and monitoring and as the load becomes distributed and some of the pain is shifted over to the storage vendors who are the authors of these volume plugins, we're hoping that it ends up actually improving quality.
More of a general methodology.
Sure.
I'm involved in the CFI. Worked through for decades. Gone through a number of standardization efforts. Last one being OpenStack. One of the things I've noticed is that instead of starting from a gap analysis, doesn't do that. Back the gaps. You have PRs for them, but version 1 is not a workable.
Version 1 is not out yet.
I know it's not intended to be, but it's like synchronous calls. There's things that we already know.
So it is completely an open source community. I want to talk to you offline just to kind of.
Well, there's contributing, and then there's the people who are making it. And right now, somebody who actually has clear to me, maybe you can.
So we actually just published a governance doc. I'm not sure if it actually. The idea is that we don't want CSI to become a war between storage vendors. What ends up happening oftentimes is that storage vendors see a standard opportunity for themselves to kind of push their agenda. We want to shy away from that. And so decided, okay, from the cluster orchestration side of things, we want to promote the best user experience. That'll be first and foremost. We kind of want, we realized what that end user experience should be like. We've kind of played around with that independently through all of our cluster orchestration system. And so a lot of the learnings from that are feeding into CSI. That said, we realize we're not storage experts. I think the feedback I'm hearing from you is that you're providing feedback and it's not being heard, and that's fair. But ultimately, the folks, we don't want to make the approvers people who have a vested interest in it. Okay. So then I think.
But I'm going from different. Replace the storage vendors who over OpenStack. Replace them with the orchestration vendors. There's a different set of vendors. The difference is the storage guys at least know storage. But they are storage experts. Would have a storage person design.
And that's fair. I don't think we're going to.
But I've noticed this.
Yeah.
That, I mean, there are conference calls you see references.
So there is basically two lists. There is the cluster orchestration list, and then there's the public list with everything. The idea is that the public list is where input is generated, and then final decisions are made in cluster orchestration system. That said, nothing is set in stone yet. I'm hearing the feedback. I'll feed it back, and we'll see if we can. I'd love to talk to you afterwards.
All
right, thank you very much.
Awesome. Thanks, Todd.
No problem.
Cool. So next up, we've got Bassam Tabara from Quantum to talk about Rook. So any questions, I guess we'll hold till the end, and then after this, we'll be wrapping up some networking. But yeah, definitely CSI is rapidly evolving. So Saad is one of the leaders in the community. Got a unique opportunity to get some one-on-one time with him after questions that you like answering during the. So let's get hooked up here. Cool. So let's hear for Bassam.
All right, can you hear me? I kind of feel compelled to say that I've worked with this community and I think they're awesome. I don't know why I feel compelled to say that, but totally responsive, taking all the feedback, making all the changes. All right, so I want to talk about Rook. If you think about CSI and the talk that Saad just gave as the front side of the house, it's about basically provisioning volumes so that they work with containers and pods and all that stuff. Rook is essentially on the back side of the house. It's the storage plane, it's the control plane for running the actual storage system. It's providing storage to volume plugins and everything else. Think of Rook as essentially running in cluster. It's not an external system, but it actually uses the orchestration. I'll walk you through it, and I'm going to do a demo, a live demo. So hopefully, demo guys are on my side. So we started this. I work for a company called Quantum. I'm the CTO of Quantum, storage vendor, but we're a friendly one. We open source this project called Rook last November in KubeCon in Seattle. Rook takes distributed storage software. We started with Ceph. You can use it for others, and we'll talk about that. And orchestrates it so it runs like a service. The main point was, how do I get my own EBS or my own S3, FS, or whatever the storage layer one? How do I run it in my cluster like I'm running everything else in my cluster? Essentially bring in the storage system into the cluster, but also do it in a way so that you don't have to kind of reinvent the stack. Go where we didn't want to go build data path. We wanted to use existing hardened, battle-tested data paths and focus more on the orchestration, integration into cloud-native environments, as opposed to spending the 10 man-years it takes to harden data path. So Rook is an orchestrator. It takes storage software. It deals with deploying them, bootstrapping them, configuring them, provisioning them, scaling them, all the things that you'd expect either scripts or an admin or a cluster admin or storage admin to do manually. Rook orchestrates and automates and uses the power of the orchestrator and power and all the services available to us to make that happen. So use the power of the orchestration environment. Run a really solid, scalable storage service. The other part to Rook is that it integrates deeply into the cloud-native environment. So we've started with Kubernetes and all the known extension points as far as I know. Essentially make it so that the storage service itself looks like it was built into Kubernetes. It kind of looks like it was in tree. There are some issues, and we're going to work through them. It looks like it was an extension to Kubernetes, as opposed to having another CLI or another management layer, another management interface. We're basically saying, it's just Kubernetes. Tell your way through. Any help? We'd like to repeat this for other orchestration systems. We're in Docker HQ. I have to pay tribute to that. But also for other storage systems. A lot of interest that people want to do cluster. Are actually actively looking at that. Rook is in alpha. Today we just shipped out of the press our 0.5 bits. Our last alpha release, 0.6 is going to be beta, and we're marching towards a production by the end of the year, hopefully, cost by QCon. That's kind of the overview of Rook. And just to motivate this a little bit, if you think about, if you look at a storage cluster here on the left, there is a lot of work that goes into orchestration environments for volume plugins and how to provision volumes. But you're on your own when it comes to storage, running the actual storage cluster. If you're in the cloud, you've got things like, Google Persistent Disk and EBS and all that stuff. If you're not in a public cloud, you're literally on your own. It's either virtual storage software, your old NetApp boxes or your EMC boxes or whatever, or it's, roll out your own Ceph cluster. What that means, if you take a use case like running GitLab. GitLab is a cool, software that you can run on. For it to run it on-premise, GitLab's awesome. It deploys using a Helm chart, runs on this Kubernetes cluster. Perhaps everything's great until it comes to, well, where's the persistent storage for it? Well, on-premise, especially underneath the Git some kind of persistent storage. And with dynamic volume provisioning, there's the machinery to provision the storage, but who's providing storage, right? And so you have to go build this on your own. Deal with a bunch of things like, how do I provision this? How do I, the availability, upgrades, backup, DR, everything else, scale it. All of that stuff has to happen manually. But even if you're on GitLab on Kubernetes in Amazon, as an example, there the storage changes a little bit. You have EBS, you have S3, dynamic volume provisioning supports this. Still not integrated. I'll show you some examples of that. You don't get the availability, you get the backup, you get the upgrades. Amazon's managing that, and you're paying them to do that. You don't get the integrated scheduling, the quality of service, doesn't work, portability. A lot of things still are lacking in that model. More concrete on AWS, if you look at, this is a chart from one of our customers. They're doing a failover across, within the same availability zone. They're running Kubernetes, failover a stateful pod that has a volume bound to it. It takes up to an hour for the attach-detach cycle to happen in Amazon. Think about all the effort that's going into orchestration environments such that you can make failover work really, really quickly, right? Down to milliseconds. All the work happening there, the ones, hours, right? An hour. Right? You think of that essentially that friction, and they're like, well, we can do better than that. And if you go across availability zones, the story is worse because you can't fail over volumes across availability zones. Amazon, you have to take a snapshot and copy it over to S3 and then restore it from S3, get the actual EBS volume to show up. So that's many hours, depending on. And then, so the aha for us was, hey, wait a minute. Distributed storage systems are distributed systems. Why not run distributed systems make them cloud native, put them in containers, mostly, turn them into microservices based, and then have them be dynamically managed by an orchestrator. And build all the logic that makes them run like completely managed. That's what Rook does. And do it in a way that integrates with the cloud native environment. So let me, I'll just skip and show you a demo, and I think that will help explain how this works. So what I have here is a little watch window. Can you guys read this? Is that an okay font? Should I make it a little bigger? How about that? Good. That better? All right. So I have a 3-node cluster. There's nothing on it. It's a bare Kubernetes cluster. What I'm going to do is use, a Kubernetes YAML file to deploy the Rook operator. The operator is essentially, this is a one-time operation. The operator is essentially the extension so that it knows how to run storage clusters. So I'll start by doing that. So you'll see the pod for the operator come up. It's now running, and it registers with Kubernetes a bunch of extensions, clusters and pools, and essentially extends the API for Kubernetes flow about storage systems. And is actively sitting and watching changes to the act on them. Now that the operator is running, like I said, you do this once per cluster, once per your Kubernetes cluster. I'm going to go ahead and create a storage cluster. Storage cluster is essentially a set of nodes and devices, storage devices that you want to bring together to create a storage cluster. decide which ones you want to be in, all declaratively through essentially a deployment spec. So here you'll see I have a cluster. It's going to be called Rook. I'm going to use all the nodes and all the devices off, and then some storage specific things. So let me go ahead and do that. So this would be the equivalent of, say, hey, I want my own S3, or I want my own EBS store. It would be somewhat equivalent of that. I'll create the cluster. And again, I'm using kubectl. There's no API here. It's literally just making changes. Create the cluster. The Rook operator is watching and looking at the changes that happen in API, and you'll see it take the declarative statement that I told it to do, which is, hey, go run a new storage cluster, and go act on it. So it'll go deploy pods using the Kubernetes API. It'll set all sorts of affinity on them. They're running well on those nodes. And, you know, cluster, essentially, I have 3-node cluster. You can see the F deployment cases, monitors, 3 OSDs. Now I have a storage cluster. Let's actually go use it. What I'll do next is I will create a pool. And a pool is a virtual concept, just like most other storage systems. And in this case, you'll see that I have a pool. I'm going to create a replication. I can do erasure coding or others. But I'll just say a replication. And for now, I'll just say size of one replica. So it's not very safe pool. But I'll also create essentially an API, an instance of an object called storage cost. Saad was talking about that earlier, which essentially sets a quality of service or an SLA around the kind of storage. And I'll link it to the pool in my storage cluster. So by doing this, I can say, you know, in this case, it's the Rook block one, but you can have, say, a fast pool or a slow pool or whatever. And that, by attributing it to the Rook provision, the back end, the storage of that is essentially implemented within the cluster. Let's go ahead and do that. At this point, I have all I need. I now have a functioning storage cluster that could serve Kubernetes itself when it's creating pods and doing volume provisioning inside that cluster. All functioning. Let's go use it. So I have a WordPress app here. And the WordPress app is actually fairly simple. It's essentially a little web server. It requires some persistent storage for static content underneath the WordPress instance itself. And it uses MySQL, which itself, MySQL needs some persistent storage. There are really 2 volumes here, one underneath the web server, one underneath the So and at this point, you're looking at pretty standard Kubernetes dynamic volume provisioning. So you'll see the WordPress MySQL instance. You'll see that it has a persistent volume claim. And the storage class it's going to use is Rook block, which is associated with Google and then the storage class. That's how you link them up. Okay. This might as well could have been external to the system, but it's not. And then you specify size, and there's another one, an equivalent one for WordPress itself. Down here, under the front end. Let's go ahead and create that. Oh, I'm going to create WordPress. You should see volumes were created, bound. WordPress and WordPress MySQL coming up, the pods coming up, now are running. So what happened here is that WordPress came up, and for storage, it was using volumes through dynamic volume provisioning in Kubernetes. The volumes are provided by the other pods running in the storage cluster that are essentially being the provider for the storage. Right? So some level, this is a very converged, hyper-converged, whatever term you want to use, cluster. It's using its own storage, this deployment. So let's actually go see if it's working and then show a moment. I'll hit one of the service endpoint. WordPress. Actually configure it to make sure it's working. Again. WordPress. Fun. Let's go kill pod running MySQL. This kills the pod. You see it terminating, and it's going to get rescheduled, running. Volume is going to be the same persistent volume that was running underneath the old pod is going to be attached and reattached to the new pod. And refresh the page, everything's so happy. It's still running. Well, let me talk a little about the architecture, and then Sad mentioned this earlier. Rook is implemented as a storage controller. It's truly an orchestrator. It's run as a controller. It watches the Kubernetes API. It doesn't on that pretty much. It's listening on changes to objects that are in the Kubernetes API. Ones that we've extended, cluster pool, object store, file system. And it's acting on those. And it has all the logic, backend specific logic, that ensures that the storage cluster can run in a healthy way. That's so by scheduling pods, running all sorts of code by these pods that actually are doing the actual storage, right? And on each of the storage nodes, there's going to be a Rook volume plugin. It's in the works. That could do the attachment and eventually CSI. Rest, all the state for Rook lives in which is persistent XCD. There is no other state there. You don't need another config database to worry about how to manage that. The operator is written in a way that it sits in a like other parts of Kubernetes, constantly reconciling what is happening in the cluster versus what should happen in the cluster. So you'll see it react. You kill one of the storage nodes, or you kill one of the mons, or you kill on a new one. And does it in a way that is very specific to the storage backend, because the storage backends can be quite finicky about order of things or consistency. Does it in a way that's actually fairly understanding of. And on the front end, there is no API, there's no new management. Build your way to all of it. And we're building a really healthy community around this for this project, and we'd love for more engagement. I'd love to invite all of you guys to come play with Rook, test it out, come extend it, add your backend, or try to be as open as. I'll open up for questions and a little mobile.
Demo, if you kill
The operator is on the control path, it's not on the data path. So everything still works. Make changes that it won't react, but when it comes back up, it will. So what we do is we run the operator in HA mode, connection between them, common pattern that controller manager, and so you can have a pretty highly available system if you'd like. It's an explicit design point that the operator is not on the data path. None of the Rook stuff is on the data path. Very important design point.
Data, the volume.
Storage backend is, yes. And the operator is scheduling that with Kubernetes, lifecycle management. That stays up and running. So think of it as storage cluster is running within the positive schedule to run. The storage system itself, the storage software can survive failures, node failures. Topology aware, you can, and if any, if the Kubernetes API goes down, which it can, or if the Rook operator goes down, everything still runs, but things won't change until they come back up. That make sense?
Yeah. My SQL as an example. Say I was making an HA.
Yeah.
Where, in fact, not using erasure code. Replicas of multiple instances of my SQL not be on the same failure.
So we will honor, selectors, there's a number of ways that you can attribute on pods and storage nodes that tells us where to place it in terms of topology.
That's your proprietary extension.
It's not actually, it's using Kubernetes selectors and everything else, but plugging them into crush map.
Post affinity or anti-affinity.
There's not,
at all.
which is why storage controls are really interesting. I don't expect the storage team, I'd say Kubernetes, others to be building custom logic for Ceph or for other storage systems, but I expect a storage controller to honor, topology that each of these. So it's domain specific.
But there's no, right now we don't actually have.
It's not a standard. So right now, what we do for Rook is that we let you set selectors on the nodes that plug, and we use those to plug into topology map, crush map stuff, and that's how you get the failure domain.
It's a little clearer than.
That's exactly right. And
This actually looks pretty good in terms of the happy path case, but what sort of things do you do? Specific conditions.
operators as in people, humans.
Somebody has to make a decision what to do.
Yeah, I mean, so at some level, you can't remove a human completely. Yes, to kind of reduce the burden of what they have to do. All of this, you can interrogate logs, they're Prometheus, all of this stuff, monitor all of it, all the stuff that you'd expect. And the fallback, if you'd like, you can also fall back to by Ceph, whatever. Our hope is that we more and more of the logic that is used to create.
That's actually what I was sort of getting at, is what sort of primitive actions are you thinking toward? Operator, look at 58. You probably don't want that, right?
Well, I showed some of the abstractions. So a cluster, a storage cluster is a new abstraction. Tool is a new abstraction. Storage node is an abstraction. Object store is an abstraction. And at each of those levels, you have, right. So each of these link to which pods and everything else behind it. Really can interrogate, you know, where is my data hosted, which nodes are providing that. Set it up with the topology questions and others, then you can actually survive node failures. Maybe beyond that, like in terms of, say, how do I know how much of a given pool is covering right now? Kinds of operations. More of those are going to be exposed through metrics. And we'd hope that actually close the feedback loop, that take those metrics and feed them into the controller, storage controller, so that current health of a pool, current state of a pool. Those things can become automated, just like we automate, say, pod rescheduling or failover. That's why, and that's essentially why we built this as a reconciliation loop. That you can take, you know, it's not taking past knowledge of the system, it's taking current knowledge of what's out there and the desired knowledge of what should be there and trying to reconcile them. So you can imagine that getting more and more complex over time. But it is fairly primitive as it stands. But no, it was using local storage. Yep. And where's
And then you're relying on.
correct.
Okay.
I mean, you could, if you wanted to, use any of the other dynamic volume, but it kind of seems like it defeats the purpose to do that. Having storage systems layer doesn't make a lot of sense, both performance-wise and cost-wise. Yes, in this example, it was running directly on local storage. At some level, the value of storage systems is they take unreliable local storage and turn it into highly reliable, you know, storage that others can use. So have a Rook container. Here's the Luminous. We work very closely with the CNCF community. They're awesome. There's an effort that, you know, there's another effort for containers and stuff. It doesn't have an operator approach like we're doing a storage controller. Focused mostly on packaging. There's packaging. Definitely. It doesn't do it now, but that is definitely on the roadmap. That's a huge pain point. Yeah.
The normal.
Right. We're done today. And stuff is, the Blue Store stuff is awesome. It takes a raw device, doesn't need a file system in between. Essentially raw IAPS. We've tested it and perf tested it, and it's. I can't share all the performance details. It was, for object storage, we saturated a 40 gig network. I've not tested perf test. Obviously, we run block, but we've not done perf testing. It's there. It's now stable in Luminous. I think they're actually due tomorrow. Tomorrow will be the day or two, as I hear. Stable, EA, and it'll be the long-term release of stuff for a couple of releases.
What a question? Yeah.
Yeah, so think of Rook as a storage orchestrator. It's the logic to orchestrate. Obviously, a lot of the logic can be domain specific, but some of it actually I think fairly generic. Instructions are creating the integration. So, we started with stuff from a selfish standpoint where we're trying to ship products based on this, better on stuff. And we've had a lot of community feedback there. Especially file systems, where people are really picky about the file systems because they vary in features. So Gluster comes up and HDFS come up as we're looking at those, quite honestly. We're trying to work with the community and getting some more people to come help with this. We can't do it all. So. That's a good question. So far, we've only focused on open source. I don't know.
License.
That's right. So you could argue that, but then it becomes an engagement beyond the open source project. It becomes more of a biz dev and relationship. That's a commercial relationship, I think. I'd have to think about it with quantum, and with my quantum hat on, not with my hat on.
Oh, yeah.
From a Rook standpoint, I don't know if it makes sense to run commercial software within Rook from a because think.
Why?
What's that?
Why?
Oh, it could. I don't know. It might make sense. Licensing and other stuff might get in the way, but sure, we can talk about it.
Petabytes of data.
Right.
Accessing the same.
That question is probably more around Ceph, and is the question, can Ceph support a single volume with petabytes of data, thousands of clients? Depending on the workload, is it a read workload or write workload?
It is an ETL job.
Yeah, so write workloads are kind of interesting. I question if it's an ETL job, I question why you're actually doing that. But
Well, it has
right, yeah.
a way to reduce.
Healthy tension between performance and consistency. I don't think anybody's solved that, quite honestly. So it's a trade-off. So
It's a,
Yeah, so I'm just wondering. Stuff is also policies like.
yeah, that's a very good question. So there's a clarification. Ceph is actually not in the business of managing hardware. Ceph is literally boxed in. It's told which some person or some script tells it the universe of things it's supposed to touch. Put me on these devices, use those devices. You have to add another node, you have to go and muck with CLI or something, or use some Ansible or other provisioning tool to let stuff know that it's changed, right? So what we've done is we've taken that and layered it on top of Kubernetes. Very dynamic environment. Yeah, you have to deal with races between pods coming up, quorums forming, consistent issues, retries. Scaling is an interesting. Add another pod, and you want to use it as a storage node. That happens all the time in, say, but it's not. It happens fairly frequently. What should happen? Should I grow my cluster? Should I start moving all the data or the slice of data that has to be? Oh, shall I have a transition period? All those things require some logic. Today, it's usually heads and look at Rook and say, we're trying to codify that. I'm going to ship it as software. And there are some interesting policies that are built in right now, but it's a start. More and more need to come in. But this is that by layering it on something like Kubernetes, you have to reinvent how to manage machines and networks and all that stuff. You assume that that's a substrate, and it is a good substrate for them, let alone distributed storage. That was the premise.
One of the question, but the things that Kubernetes boundary of compute. Operation of mounting the volume to begin. The mount.
Well, the image can come up early, but it could take a while before you can declare it healthy.
Exactly. And,
That's right.
But Kubernetes needs to know when it's
Right.
not when it started.
That's why it's my fundamental belief. Have to have controllers.
But there's another funding for this thing.
Right. And I think actually so far we have not run into issues where there are health metrics, health hooks, termination hooks. You can fault Kubernetes for a lot of things. I wouldn't fault it for the amount of extension points
Your
available.
APIs are built to an
Much. All of Kubernetes is designed to be async. All of it.
I understand.
Yeah, I heard your comment earlier.
That's
So.
one of the reasons why I was asking.
Yeah.
Really did do the async.
Sad's just stepped out.
So you did that because the reality is you never know how long.
I don't think distributed systems can scale if they're designed.
There's a question that goes along that.
That's a function of the Kubernetes API, which is a function of etcd. So,
Long running, these could be potentially.
there are 10-minute operations. And actually, those are the easy ones. It's the millisecond operations that are harder. So the 10-minute operations are easy, right? Infinite. Long time. The millisecond operations are the ones that are tricky, and storage systems tends to be a little more tolerant of that. The difference is you're not telling Kubernetes to wait for 10 minutes. You're telling Kubernetes, go perform an action, deploy a pod, right? That completes in. Operator is running the long-running task. And the way it does that is it's actually stashing data, etcd operator, right? Full plane, essentially. Saying, okay, look, I was told to run this thing that's going to take forever. Where are we now? Where are we now?
So
Where are we now?
But you've effectively made worse. Because you're doing the long running operation.
Not in a generic way, in a back-end specific way yet. not a generic construct that we create. In this case, like Ceph has very, we do it in a backend specific way, not in a generic way.
Basic, simple question. If I have, let's say, 1,000 nodes, and I'm running, WordPress is connected.
Well, it depends. For Ceph, it kind of depends. So typically what happens is that you, now Ceph specific, right? Ceph, there's all the storage of 1,000 nodes. Right? What you do is you create a pool of a rule for how to select which subset of nodes you want to be part of. That's arbitrary. It could be ones with SSD drives, ones with blah, 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 right? Memory, or, it can be very specific. And then within that, it's declustered. So every bit of data you write into that, that's depending on your replication settings, distributed subset, but only to the replica or erasure coding onto that number. So in a concrete example would be, I have 1,000 nodes. I have a pool that subselects 100. My replication setting is 3. Every time I write an object to that pool, 3 out of the 100 nodes is going to get 3 changes every time, for every write. Oh, yeah. So there now you have to deal with affinity. You could do that. You could say, I want, for these nodes, I want to create affinity rules so that my MySQL is separate from mine. In a converged way, but spread your data across fault domains. Both are possible. Lots of questions. Thank you. Yeah. Thanks, guys.
Awesome. Thanks, Bassam. So I think we're going to get kicked out of here around 9:10. So feel free to network and get to know each other, talk with the speakers. Thanks, everyone, for coming. We'll probably do this on a monthly basis, maybe once every other month. Just shout out to Cloud Native Computing Foundation for sponsoring, also for Rook for sponsoring the pizza and the drinks. And we'll see everybody next time. Thanks.